Hello, my name is Christian Pedrigal,
And I'm Antonio Cervantes.
and this is the segmentation for drone safety landing system, predicting safe landing locations of aerial drone images using UNet classification models. Many major retailer companies, such as Amazon and UPS, have been approved by the Federal Aviation Administration, FAA, to deliver 5-pound delivery packages in lightly populated areas using UAV, or commonly quadcopter drones. This is a major milestone for the feasibility of the drone market by helping boost these retail, healthcare, and food industries. But the question is, how trustworthy are these drones to be carrying weighted packages for and above people? Drones are, in engineering aspects, are essentially nonlinear models that rely on states of unstable equilibrium, relying on many sensors such as GPS and IMU that work together to observe the states of the drone is very complex and can oftentimes lead to inaccuracies, or worse, create many failure points in the system. These failure points include GPS errors, loss of signal, software malfunctions. Drones, in short, are a harder engineering problem to solve, plus given the fact that they may hover over people, pose a necessary requirement to implement safety features for emergency landing situations. This idea of implementing safety landing protocols is not common. NASA's Perseverance rover used machine learning and computer vision algorithms to produce a real-time autonomous landing navigation in 2021. Also, more recently, university researchers developed a CNN to segment parts of a simulated drone footage. As Antonio will discuss soon, we'll be applying the same data set from these researchers, but unlike their use in a video game, we will be using a real-life drone footage to investigate the practical outcomes from this methodology.
Our project's objective is to use the UNet segmentation architecture to determine safe landing locations. To make a unique contribution to this field, we want to test our model with real drone footage to see how it really works and validate the previous work of other researchers. We also want to make our code modular and implement unique post-processing techniques as well. Our data is from the TU Graz Semantic Drone dataset. It contains 600 RGB bird's eye view images with 23 different labeling classes. The data also contains mask labels that segment the objects in the images with certain color intensities based on its label. The plot here, you can see the RGB images on the left and its mask label image on the right. Our code was based on several open source frameworks, and most of them were in Jupyter notebooks. The main things that we grabbed from them were data preprocessing functions and training and model architecture. Our original work was converting the code into modular scripts that could be implemented on the HPC cluster for use of its GPUs. We also made some interesting post-processing visualizations, and we tested different scenarios of real-life drone footage. The data preprocessing methods we used consisted of data augmentation. This is where images are flipped, rotated, and cropped into multiple images. This was done because our original data set had images of very high resolution that would probably overload a GPU with just one image. So making low resolution images, multiple low resolution images, would make up for that one. The image on the right show an example of how one image is augmented. Now I'm going to hand it back over to Christian to talk about our code modularity.
Thank you, Antonio. We utilize a modular-based code structure for an efficient project development and for good team project practices. This allows for independent workflow and easy code debugging. Shown on the right, we see the source directory, which involves scripts that train the model, and under it, a utilities directory that includes function scripts. For semantic segmentation, we used a UNet architecture, or better known in class curriculum as an autoencoder framework in CNNs. Autoencoders are great in areas of unsupervised learning data sets, where the data is first encoded into its most important features, which in the diagram is the bottom of the U, and then later decoded back to recreate the original images as a way to validate the accuracy of the model. I won't be going into the details of the network architecture, but we use a series of convolutional layers, hash normalization layers, and max pooling layers. The optimizer selected was Atom, simply because it's a good combination of RMS prop and SGD with momentum, as well as it works well with large data sets. The loss was clearly categorical cross entropy, since this is a multi-class classification problem, and the learning rate was scaled down to a factor of 10, as well as the batch size was chosen to a smaller value in hopes to more accurately training the model. Set to 40 epochs, the data was able to finish its training at epoch 37 using early detection, which is when the accuracy of the model is settled. One statistical method to validate the model is the combination of training accuracy and loss plots. This is used to visualize the training and validation accuracy and to inspect if there was any signs of under or overfitting. From the hyperparameters aforementioned, the model was trained to 85% accuracy on the HPC GPUs. There's no overfitting because there's no large margin between the training and testing curves, and there's no underfitting because the curves reach low logarithmic loss values that are satisfactory for multi-classification problems for 20 or more classes. One final step in this semantic segmentation was to add text labels in post-processing to the classified areas of the video frames. In the left two images, you can see that the video frame properly segmented the landing zones as their proper category: paved areas, dirt, grass, and gravel. On the right, you may see the contour plot and the raw segmentation of the video frame across the 23 categories. Now that I finished talking about the setup of our code, the model architecture, and the labeling of the images, I'll hand it to Antonio to discuss the experiments that took place for training the model.
Thank you, Christian. So we ran some experiments with the drone and the UNet model to see how shadows from objects and the time of day affect the model's performance. In this video, it was shot at midday where the sun is directly above and there's no shadows. And you can see that it's pretty good at detecting the tree and car in this video. Next, we shot a video in the morning where there's sun and there's dark shadows. And you can see that the car is not visible, and actually the entire shadow is labeled as an obstacle. Finally, in this video, we shot this in the evening where there's a lot more shadows, but they're not as dark as the one before. But you can see that the predictions are not working well, and it's actually labeling the street as an obstacle. Next, we wanted to see how well the UNet model can detect people. In this test, there's no shadows, and the model accurately detects a person walking across the street. And in this test, there are shadows, and the person is also accurately detected. So we think this is because the camera's auto exposure was enabled, making the colors in the frame appear correct, leading to good performance. So this led us to believe that camera lighting is an important factor in segmentation modeling. So now I'm going to hand it back over to Christian to talk about our labeling process.
One important parameter that was involved in adding text labels to the segmented areas was the filter size in creating the labels. In short, the filter size would determine the sensitivity of the segmented areas, whether or not the smaller areas in the video frame should be edited or not. In this case, working with larger filter sizes of 60 pixels worked compared to smaller sizes such as 45 pixels because the 45 pixel filter sizes would allow for noisily classified areas to be then labeled. You can see this effect in the right image where the paved road would be labeled vegetation and gravel compared to the left image where there would be no labels at all. As Antonio showed during his experiments, lighting conditions do play a large role in the accurate semantic segmentation of the drone footage. The best lighting conditions for the drone are in bright conditions, which follows our intuition where lighting conditions are generally better in image classification problems. The contour plot on the right best showcases this in showing the distribution of the classified areas across the full color bar. While lighting conditions aid in improving model accuracy, there are still some inexplicable findings from our data analysis. We found that certain color choices of many building rooftops correlate to higher accuracy. Particularly, the colorful blue and red rooftops were able to be properly segmented, where the gray rooftops were ignored. Lastly, the gray paved area, which was the most segmented label, wasn't sensitive to its road conditions. In the figure shown here, tire markings would affect the segmented area of the paved area. This is not true, and the drone would be able to safely land in these areas of the zone, which include the tire markings.
Another conclusion that we found was that there's a need for more data in shadows or low light conditions. Even with camera auto exposure tests from before, there's still going to be situations where cameras just can't illuminate a scene properly. So having more training data in low light scenarios would help greatly. And finally, the broader impact of this project is that having more safety features in drone delivery will help bring them to reality. Segmentation has the potential to aid in safe emergency landing because it prevents drones from landing in dangerous areas. There was a case where a delivery drone in Switzerland almost crashed into a group of kindergartners after having a GPS malfunction. So having a deep neural network and computer vision system as a backup would be a great safety tool. And using segmentation can also improve delivery efficiency by landing right at someone's doorstep, for example, instead of landing in a designated landing pad. This could increase delivery speed. So we just want to say thank you for listening to our presentation, and we hope you have a great day.